Hi, and welcome to our presentation. I bet that many of us have had the experience of driving our car and suddenly somebody swoops in right in front of us. Or we're driving on the highway and the car in front of us is driving below the speed limit. Driving styles are crucial in traffic, not only for human driving. If we consider autonomous vehicles, driving styles are crucial for passenger acceptance and trust. Yet many autonomous vehicles tend to drive overly defensively, limiting their efficiency and passenger comfort. So how do we encode driving styles into motion planning for autonomous vehicles? And how do we calibrate them such that the resulting behavior is perceived as intended? My name is Sanne van Waveren, and I'm delighted to present our work on encoding human driving styles in motion planning for autonomous vehicles, which was led by Jesper, Karlsson, and myself in equal collaboration. One way to incorporate driving styles into autonomous vehicle behavior is to learn them from actual human driving data. However, recent work has demonstrated that people's preferred driving style for an autonomous vehicle may not necessarily match with their own actual driving style. To incorporate driving styles into motion planning, we can also adapt cost functions and constraints. For example, we can favor smooth accelerations, which will lead to increased passenger comfort. But it can be difficult to model complex aspects of driving styles into a single cost function, and constraints are often used in a strict fashion. For example, to ensure safety, like in lane changes, and road compliance, for example, when there are curvatures in the road. However, in some situations, the autonomous vehicle may need to violate a certain rule for a certain period of time. For example, in this case, the car needs to cross the lane markings to take over the car in front of it. In such cases, we might need some softer constraints. This can be achieved by modeling constraints with temporal logic. In this work, we use signal temporal logic, which in contrast to other logics, allows for quality evaluation of a proposed solution. In other words, it can evaluate how much and how long a trajectory violates the specification. In our prior work, we have used syntactically co-safe LTL to encode traffic rules. We can then determine trajectories that minimally violate these rules by assigning costs to the potential violations of each rule. In situations when not all specifications can be strictly guaranteed, such least violating motion planning approaches attempt to find a motion plan that minimizes the violation over the set of specifications. We previously proposed the following cost function that encodes the importance of mission time against the satisfaction of spatial preferences. The function uses two parameters to denote the lowest spatial robustness allowed, alpha, and the pace at which the trajectory is penalized as it approaches the lowest allowed spatial robustness, A. However, these two parameters of the penalty function were manually calibrated, and it remained an open question how to calibrate these two parameters. Therefore, in this work, we focus on calibrating these two parameters such that the resulting trajectories reflect distinct driving styles. The contributions are as follows. We provide STL formulas for the responsibility-sensitive safety model, which is a formal model that defines what it means for an autonomous vehicle to drive safely. We also provide a parameterization of the cost function that results in distinct driving styles. Now let's talk about this parameterization of the cost function. Recall the cost function we introduced before, which is a positive function that expresses the compromise between a time-efficient trajectory and one that prioritizes spatial preferences. We implement a motion planner that uses this cost function to support spatial temporal constraints. We run our motion planner with different calibrations of alpha and A. For each resulting trajectory, we then computed an objective defensiveness score as obtained from prior work. This defensiveness score is computed from 9 features, 8 of which are adopted from prior work. And one additional feature was added to incorporate the chicane scenario we used in this work. Examples of such features include mean distance to the leading vehicle and maximum speed of the ego vehicle while turning. Each feature was then normalized using min-max normalization. We then averaged over all features to obtain a defensiveness score. We categorized the defensiveness score into bins that correspond to a certain driving style. Now let's look at some examples. Here we have a roundabout scenario. Notice that the aggressive car enters the roundabout the first, followed by the neutral, and the defensive one waits the longest before entering. In the intersection scenario, notice the difference in velocity between the three cars. Again, the aggressive one enters the intersection the first, while the defensive one waits the longest. In the overtake scenario, notice the difference in the distance towards the car while overtaking in the neutral and aggressive example. The defensive car decides to stay behind the car in front of it. In the chicane scenario, we have the same difference in velocity. We can see the aggressive car drives the fastest. The neutral car still decides to go first before the upcoming car, whereas the defensive one decides to wait for the other car to pass first. Now let's dive into the evaluation of the resulting trajectories. We recorded traffic scenarios in the Carla simulator with different parameter calibrations. We then asked participants to evaluate each of these scenarios in an online study. We associated driving styles to different sets of parameters. We used 4 different scenarios in this work: a roundabout, a junction, a chicane, and a takeover scenario. Participants saw the scenarios both from a top-down perspective and a driver's seat perspective. This was because the perspective might influence how the defensiveness of a trajectory is perceived. We asked people to rate the perceived defensiveness of each trajectory on a 7-point scale. Then, we also asked people to indicate their preference in a pair of trajectories using a 2-alternative forced choice answer format. We additionally collected information on people's personality traits and self-reported driving style, as these personality characteristics may influence what driving style people preferred for their autonomous vehicle. In total, 35 participants rated these trajectories and preferences. Participants possessed a driver's license for almost 18 years on average. And all participants had heard of autonomous vehicles or self-driving cars prior to the study. So we asked people to rate the defensiveness of a vehicle's behavior in each scenario. And we asked people to indicate their preferred trajectory in this forced choice format that you see on the right, where we display 2 trajectories side by side. Let's first discuss the results of rating the driving behavior. Were the trajectories perceived as intended? Results showed that participants perceived the parameter calibrations as intended. As you can see in the graph on the right, the aggressive driving style was rated as least defensive, whereas the defensive driving style was perceived as most defensive. Neutral was rated in between. This quantitative result was also reflected in how people motivated their choice. For example, this participant wrote, "While I can appreciate patience in a car, there is such a thing as too defensive when driving, which can cause accidents much the same way being overly offensive can do." Now let's look at the preference ratings. Participants saw a preference pair, either aggressive versus neutral or neutral versus defensive. They rated each scenario from each perspective twice. Once starting from a low defensiveness score and ending with a high one, and once the other way around. Whether a participant would see a scenario from a low or a high score first was counterbalanced. The left-right placement of the videos was randomly determined. Results showed that participants converged to a more defensive driving style if they started from a high defensive video, and vice versa. This was regardless of whether they saw the video from a top-down view or a driver's seat perspective. Interestingly, people who self-reported to be conservative drivers tend to prefer a more defensive driving style for the autonomous vehicle as well. So in this work, we demonstrated that we can leverage human driving styles in synthesis of signal temporal logic specifications and parameter learning. A major strength of these formal method-based approaches is that they provide verification of encoded specifications. And so it will be possible to guarantee that the driving style will hold for the entire lifetime of the system. An interesting qualitative finding was the mention of aspects such as patience and respectful driving in people's motivations for the preferred driving styles. This implies that further research should consider that certain normative behaviors, what is deemed acceptable and appropriate, should be incorporated in autonomous driving etiquette. Finally, we encoded only a subset of traffic rules from the RSS model. In the future, encoding a larger set of traffic rules will allow to represent a larger subset of driving patterns. This goes hand in hand with a more fine-grained analysis of the individual and combined impact of each of the specifications on the resulting driving styles. To conclude, we can successfully encode driving styles in motion planning for autonomous vehicles, and the resulting trajectories are perceived as distinct driving styles. This highlights the possibility to leverage driving styles in autonomous vehicles while keeping formal guarantees. It paves the way for autonomous driving that is guaranteed to be safe while facilitating increased user acceptance and trust. Thank you for listening. If you want to read the full paper, you can scan the QR code right here, and feel free to contact us if you have any questions.